Tom, recently there's been some exciting news out of Australian National University. An experiment's been carried out by Associate Professor Andrew Truscott with PhD student Roman Kakimov, a delayed choice experiment that was a thought experiment proposed by physicist John Archibald Wheeler. Now, he proposed this thought experiment long before anyone could carry out this experiment. He's the person who coined it from bit. Can you tell us what this experiment is about? How can you explain this, and what does it mean to MBT science?
Okay, sure. John Archibald Wheeler also was famous for coining the term black hole. He's a very famous physicist. He died in 2008, I believe, in his 90s, mid-90s maybe it was. He was some of the best quantum physicists that turned out later, such as Richard Feynman, were his students. So he was very productive in his life, a very brilliant man, very highly regarded in the community. And in the last third of his tenure as a very high-profile physicist, he decided that all of reality was virtual, based on information. And this is when he coined the frame, it from bit. It being everything, the whole universe, and bit being bits, from binary bits. So he was convinced that reality indeed was just information. Okay, well, let me explain a little bit about what his thought experiment was about. Okay. Now, this experiment is very similar to the double slit experiment, not in the way the experiment works, but in the results. And as I go through this, you'll see the same words that we use in double slit will be coming up again here. All right, this is what's called an interferometer. Big name, but it doesn't really amount to too much. There's only two elements in it. There's mirrors. Here's a mirror, and here's a mirror, just a regular, everyday mirror, so that when light hits it, it reflects. Here is a special mirror that's sometimes called a half-silvered mirror. And when light gets to this mirror, if you shine a beam of light on it, half the light transmits through that mirror, because it's only half silvered, and goes this path, and the other half gets reflected by it and travels this path. So we have the red path and the blue path as light beam is shown on that. Now, if you fire just a single photon at it, the photons half the time will be transmitted through this half-silvered mirror and follow this path, the red path, and the other half the time they'll follow this blue path. They'll be reflected here rather than be transmitted. Okay, so this is the nature of this element. Well, what physicists did is they made these two paths exactly the same length, so that a particle who decided to go this way would travel just the same number of wavelengths as a particle that goes this way, so when they got down here, they would be in phase still. Okay, that means the peaks and the valleys would match up. So what they saw is they would fire one particle, could be an electron, could be a buckyball, could be a photon, just a particle of some sort. They'd fire one particle in here that this arrow indicates, and when it comes in here, it would do one of two things. Because a particle can't go half of it one way and half of it the other. Particles don't do that. Particles are whole particles, right? The electron is a whole electron. So the particle would either go through this way half the time, and when it does, it comes down here and hits this detector. That's a detector. And the other half the time, it would get reflected, come down this path, hit this mirror, come over here, go in this detector, the blue detector, and be detected. So let's say you'd fire 1,000 electrons at this. Photons would work too. You fire 1,000 particles, and 500 of them would end up here, and about 500 of them would end up there, you see. So half of them would follow one path, the other half was the other, because there's a probability, a 50-50 probability of whether it goes through the mirror the half-silvered mirror gets reflected by it. All right, well, that was well and understood. Now, the second part of that experiment, well, first, that's what we're showing here, is that all of the data, all of the particles that get detected here or here, they all fall in one spot. This is a number of counts, number of particles going on this axis, and position going on this axis. And a certain position, all the particles would pile up in one spot. Or if you want the view of actually looking at dots on a screen, all the dots would pile up here in this spot. Okay, so this is a bunch of little dots. All right, now they had a second experiment, exactly the same as the first. This is Wheeler's Gedanken experiment, means thought experiment. And he just added one thing. He put another half-silvered mirror right here, just like this one, but now it's down here. Okay, now what that does is that if a particle comes through and just happens, 50-50 chance to take this red path, hits the mirror, comes down here, hits another silvered mirror, which is a 50-50 chance of going straight through into this red detector or being reflected going into this blue detector. And if it comes down this blue path, hits this mirror, gets here, it has a 50-50 chance of being reflected down to this mirror or being transmitted through this detector or being transmitted through to the blue detector. So now you see each path has a 50-50 chance of being in each detector. Well, you should recognize that as far as double slit goes, that the which way information has just been erased. You see, here we knew which one it came from. If this detector got it, it took that path. If that detector got it, it took this path. We know exactly which path it took. So all we get is all the particles pile up in a pile. There's no diffraction pattern. Here, we don't know which path it went through when we get out to this detector, because it goes through either path. It has a probability of 50-50 of going to either detector. So there's no differentiation between the paths anymore. What happened is when they send single particles in here one at a time, they got a diffraction pattern. These particles would come in here and create this diffraction pattern. And here I have a picture of it, just like this one, where it's number of particles that hit by position across here, or if you just think of it as hits on a screen, there's a lot of dots under this big, and a little fewer here and a little fewer here. So the amplitude goes down as you move out, but you get a diffraction pattern scattering of the particles. So the particle comes in, and one particle goes in, and some particle will hit somewhere on the screen. It might be here on this line, or then this line, then that line. They just hit wherever they are, and eventually you send enough particles through and it defines this diffraction pattern. Okay, it does this. This is really like the probability function here. All right, so that was the experiment. And everybody knew at that time that when you did these two experiments, when you did this one and the which way information was available, you got two piles of electrons at each detector. And when you did this way, where the which way information wasn't available, you got diffraction patterns. See, it sounds just like the double slit experiment, but it's just a totally different mechanism, a different experiment. So what Wheeler did is he said, well, let me back up. What the physicists said at the time was, well, somehow, when this particle comes in here, it knows that this is a particle setup. See, they said light could be a wave or a particle. And eventually they said electrons could be a wave or a particle. And that buckyballs could be a wave or a particle. Anything can be a wave or a particle. And they said the principle of the complementary principle said that it only acts one way or the other. It can act as a wave and a particle. It can act either as a wave or a particle, but it can't do both. They're complementary, but they're mutually exclusive. That's what the science said. So, when this was set up this way, where this detector collected from this path and that detector collected from that path, okay, that was an experimental setup where they were going to see particles. Send a particle in, They either get a detection here or they get a detection there. The only two probabilities. So they pile up here, they pile up there. Now this setup with a half-silvered mirror there and a half-silvered mirror there, the which way information's gone, and they said then somehow this particle going in here knows that this is a wave situation. Like here it's time to be a particle, and here it's time to be a wave. And when it's a wave, then the wave can take both paths and interfere with itself and get a diffraction pattern. But of course, in order to say that, that kind of made sense, except this is a single particle. How does a single particle become a wave that can go through both slits at the same time, take both paths, because that's what it has to happen in order to interfere with itself. You can't take an electron or a buckyball and have it turn into a wave that can take both paths, okay? This is what was thought. So what he said, what Wheeler said, he said, well, if this particle is so smart that it knows this setup is going to want it to act like a wave, and over here this particle is so smart it knows that this setup will want it to act like a particle. Remember, it can only act as one or the other. And this particle now has to be smart that it knows the kind of experiment that it's going into, which is kind of ridiculous, right? Then, but physicists were backed up against the wall, so they had to be ridiculous because that's the only way that they could explain this, was with being ridiculous. Anyway, so he said, when does the particle figure out that it needs to be a wave or a particle? This was his experiment. So he said, here's what an experiment should do. We're going to put a particle in here, and there will be no mirror at this point, no half-silvered mirror. So it'd be this case. We're going to put the particle in, and the apparatus looks just like this. Well, it then would know that it needs to be a particle, right? And it needs to know that right here, because if it's a particle, it can only go one way or the other and end up in one detector or the other. Now, after it comes in here, it has to have already made its decision what it's going to be, because if it's a wave, right at this point, it has to part go that way and part go this way so it can interfere with itself. So that decision of whether it's a particle or wave has to be made right here, because it's different. Particle goes one or the other, a wave goes both. So he said, aha, we'll start this experiment and we'll put a particle in here in this form. And then while this particle is moving down this path, it's somewhere in the apparatus, hasn't gotten to this point yet. It's here or here or here or here, someplace just in the apparatus. We're going to stick that mirror in down here. So now you have to be very fast to do that. You've got a particle of light going at the speed of light, and it's traveling these lengths. And after it enters here and gets somewhere, say on either of these lines, then you want to stick this in, because it's already made its decision whether it's a particle or wave at this point. Now, if it comes into here, it says, well, this is a particle setup, so it should choose to be a particle and go to one or the other. Now, while it was in process, somebody sticks a silver mirror in here, it's already decided to be a particle. What's it going to do? You see, that was the problem. What is it going to do? It's already had to decide at this point it's a particle and go in one or the other, because that was this setup. Can it know ahead of time that somebody's going to switch it? Well, that would be a very smart particle, wouldn't it? Can tell the future. So that didn't make a whole lot of sense. So this was his thought experiment. Nobody was able to do it for a long time, because it's very, very hard to stick a mirror in here or take it out faster than light can go around that corner, you see. So it stayed a thought experiment for a long time, until some very clever people in Australia figured out that they could simulate these half-silvered mirrors with dual laser beams. They'd make a diffraction grating, which is what this half-silvered mirror works like, out of dual laser beams. And a laser beam can be turned off and on very, very quickly, you see, because the laser's right here close to emulate that, and the laser's right here. So a laser light only has to move, just a tiny little bit to get to that slit, while this thing has to go all the way around the circle, so the light could produce this extra mirror down here or take it away. Now in this experiment, they had those lasers turned on randomly. So they'd let the particle come through here. Now the particle's in the apparatus. Now a random number would be drawn, and based on that random number, this mirror would be stuck in or not stuck in. You see? That's the way they did the experiment. Well, what is this poor particle going to do? It gets to the thing, it gets to this apparatus, it says, oh, this is a particle, I need to be a particle, I'll go one or the other. So it picks one, say it picks this red one, and then somebody throws a new mirror in here that wasn't there before. Now what does this particle do? It says, oh damn, I'm in trouble because I decided to be a particle and I really needed to be a wave because I know that when this happens, that's the answer. So what they did is they did this experiment, and sure enough, they always got diffraction patterns. So here's that diffraction pattern, and this is amplitude versus position, or these are just spots on a screen. I did it either way you're used to looking at it. And this detector also got the diffraction pattern. And every time this mirror happened to be there, they always got a diffraction pattern. Every time this mirror was not there, like this case, they got spots. One spot in one of these cases. So here, let's say they throw in 1,000 spots in this case. They would have 500 of those spots just happen to land in these stripe patterns and nowhere else. And the other half of them would just happen to land in this diffraction pattern, you see, because there's a 50-50 choice down here. All right, well, that was the experiment. Well, of course, so it's just like the double slit, except it's done differently. But that tells you that this result is not simply an artifact of the double slit experiment, that it's a fundamental part of the way reality works. It works this way just like it does in the double slit in a completely different experimental setup. So we know it's not, well, you get those double slit results because something funny about that double slit experiment. Well, we get the same results here, and this has nothing to do with double slits. So then the question is, what does MBT say about this? Well, it's the same answer as it was for the double slit. There are no particles. And when you talk about, you put a particle in, and you have to then have a particle go one way or the other, it creates this inconsistency because they're not particles. Particles are not particles, they're probability distributions. So you have and that means it's just a probability of a potentiality. You have a potential for a particle to go this way, and there's a potential for a particle to go that way, but because it's just potential, the potential of which way it goes can go both ways. So the probability can go both ways. It's not that waves go both ways, particles don't. It's that the particle is just a probability. It's not really a particle. Okay, it's a probability. And that probability has a potential to go either way, so there's a certain amount of probability that goes either way. Now that probability gets around here and it gets to this, well, now, if it's coming this direction, it has a probability to take a reflection and go here, or to go transmission and go through here. So the probability to do either, that probability splits. The probability that's gone this way splits into those two probabilities. The particle doesn't actually appear until it hits the detector. That's when the measurement's made. And when the measurement's made, oh, you get a particle. Now, where is that particle going to hit? Well, there's a probability that it could have gone either way. Those probabilities interfere with each other, producing a different probability pattern, which is what this looks like, this kind of wavy looking thing here. That's just a probability as a function of position. It's another way to look at it. Probability as a function of position. You say this is probability, that's position. So now you have this pattern, this interference pattern, that is just a probability of where the particle might hit, because of the fact that you have the probability of potential particles going both ways. They're all potential particles, no real particles in this thing, until the measurement's made at the detector. So the first sign of a real particle is when that detector gets something. So you fire a particle, and one of these two detectors will get a hit. You fire a particle, one of these two detectors will get a hit, just one of them. Fire a particle, one of these two get hit, and you do that. Fire 1,000 particles, and about half of them will have ended up in this detector, and about half of them will end up in this detector, and the half that end up in this detector make a diffraction pattern, and the half that end up in that detector also make a diffraction pattern. You see, so that's the thing. So when that particle hits here, suddenly the probability has to collapse to a real particle. So you have this probability function that looks like this, and you say, all right, where's the particle going to hit? Here's all the places it could probably hit. It hit at this peak and that peak, but what about these things in between the peaks? They're zero, no probability of hitting there. So the way the system works is when it hits the screen, now we have to have a measurement of something that's in the real world. Now we get a particle. The way that works is the system takes a random draw from that probability distribution. It just randomly draws out of this distribution, and when it makes that random draw, it goes, okay, particle, random draw, you go here, and it puts it there. The next one does a random draw and says, okay, you go there. And another random draw from a probability distribution says, you go over here. So you fire one, and you only get one out. But that one will either be here or here, and it'll always land in a pattern of a distribution, because that's the distribution of probability, you see. So that's the way it works, and that's what MBT says about it. It's the same explanation for the double slit. And the reason that it's interesting is for a couple of reasons. One, Wheeler said this many decades ago. He was convinced that reality was information, and that means that this was a virtual computed reality. Very smart man. People should have paid attention to him. And they couldn't do it until recently, and when they do, it turned out just as Wheeler predicted, because he said it won't matter what the state is in when it comes out, because sometimes they left this thing in. You see it down here. They left this half-silver mirror in, let the particle come in. It knew now it should have been a wave, but before it got to the end, it pulled that mirror out, and now it had to be a particle. You see, it did the reverse too. That's why the random number could put this in or pull it out. So it works both ways, and Wheeler said it doesn't matter. He says whenever it happens to be in when the particle gets there, you'll get a diffraction pattern, and whenever it happens to be out when the particle gets there, you'll get these two piles. And the only way that works is if particles are not particles, because particles can't do that. Therefore, a materialistic view of the world as it's built up of particles is nonsense. It does not work that way, and this experiment and the double slit basically tell physicists is that the materialistic view, the material reductionism, that everything is built up of particles, and all the little particles make bigger particles, you know, the subatomic make atomic particles, which make molecules, which make stuff. So everything's built up of these particles. It's nonsense. That materialistic view is just wrong, and these experiments show that it is wrong. Particles aren't particles.
Tom, as Professor Truscott said, it proves that measurement is everything. At the quantum level, reality does not exist if you're not looking at it.
And what he meant when he said when you're not looking at it, he means if you're not taking a measurement, if you're not making a measurement which requires a particle to come in, you see. Now the reason that works is that this is a virtual reality. If it's a virtual reality, it's just like any other virtual reality. There's some basic concepts of virtual reality that explain this, and that is that you have really two active elements and a third element that's not active to make a virtual reality. One, you need a computer to compute the virtual reality. Okay, that's one active ingredient. Two, you have the virtual reality that's computed. Okay, it computes a virtual reality, and there's the virtual reality that's computed. But that's an inactive ingredient. That's just ones and zeros on a hard drive. Okay. The second active ingredient is you need a decision maker. You need a player. A virtual reality is of no value without a player. So you have a computer, active, a player, active, and the computed virtual reality itself. Okay, those are the three elements. Now what's going on there is that the player and the computer are sharing data back and forth, right? The player says, elf, run away. And then the computer makes the elf look like he's running away in the virtual reality. So now the danger can't get him. Or he says, computer, I want my elf to fight. So then the elf makes the computer makes the elf go into the fight, and now he might get damaged because there's a fight going on, you see? So it's a data stream between the player telling the computer what the character does, making the character's choices for the character, making all the character's choices, and then the computer telling the player what the consequences of those choices are. Because the computer has a whole bunch of players, not just this one. It has lots of players in this game and other characters and things in the environment. You know, that elf has to worry about the trees and the rocks and the water and other kinds of things. So the computer knows where everybody is. So the player says, computer, here's a choice I make for my character. And the computer sends back, okay, this is the consequences of that choice. Then the player says, well, then I'll make this choice. And the computer says, well, here are the consequences for that choice. And that's what's going on, this dialogue between the player and the computer. The actual virtual reality is just ones and zeros on a hard drive someplace. Now, the thing that's interesting there is that when the computer only sends out data to describe what has happened when something's happened. The computer isn't just sending out data describing what's happening if there aren't any players. You see, if there are no players in the game, the computer's not sending any data out to anybody. It only sends data to players. So let's say all the players are gone, the computer's on idle. Nothing is going on in that reality. No data is sent. Oh, now a player logs on. And the player says, all right, I want my elf to run at that tree. Just run right into that tree, elf. So he points his elf to that tree and he sends, make my elf run into the tree. And the computer sends back, splat, okay, your elf ran into the tree, now he's hurt. Okay? It wasn't until the player asked for something, it wasn't until it asked for information, and what we can say, it wasn't until the player made a measurement, asked for data, that the computer sends him anything. The computer's not just sending stuff, if there's nobody there, right? He only sends stuff if there's players. So that's the way it is. The players are the people taking these measurements. And when the player sets up a counter like this, then this probability, this particle that's nothing but potential particle in probability, there's nothing for the computer to render yet. But when that particle gets to where it's going to hit that detector where somebody's looking for data, now the computer has to send some data because those people asked for it, because they're players. Okay, so that's why we have this thing about consciousness and the double slit experiment and the measurement problem. It's only when you make the measurement. Making the measurement is a player asking for information. It's a player demanding information. All right, my elf ran into a tree. I demand, computer, you tell me the consequences, the results. Well, here's a detector. I demand you tell me where this particle hits. Well, then the computer says, well, it hits over there. You see? So it's not until the player asks, it's not until the measurement is made, if you will, that the system, that the computer sends an answer. If nobody asks, the computer doesn't have anything to do. All the characters are just sitting there not doing anything because nobody's asking for data to describe the result of a direction to their character. Well, here's the result of this experiment. So that's why it works that way. Now, there's another interesting thing, and that is that in this triad of active player, active computer, and then just the virtual reality as ones and zeros on a hard drive, is that the computer and the player have to be in the same reality frame. Because they're talking back and forth to each other. Same reality frame. You can't talk back and forth across different reality frames. In a totally different reality, then the other frame doesn't exist. If I'm in this reality, that's my reality. I'm in that one's a different reality. You can't talk back and forth across reality frames so easily. Not a direct line like you need for a computer output. You have to be in the same reality. So that means that the player, in this case, the player of World of Warcraft, with his computer, right, has to be in the same reality as the computer, which is some server somewhere that's serving up the World of Warcraft game. Some big server somewhere in this reality frame, and a player who is the consciousness of the elf, you see, the consciousness of the scientists who set up this experiment and demand that the system give them an answer when a particle is supposed to hit that detector. Well, we know one of these detectors is going to get hit because we threw something in that end, and we know that at exactly, so many microseconds, something's going to hit one of these two detectors. All right, computer, tell us where it hits. That's a measurement. It's in the real world. This is a virtual reality. It has to tell them where it hits. And it goes up, takes a random draw from the probability distribution and says it hits there. You see? And its probability distribution looks like that because the probability could have gone two ways, and there's interference between the two ways that it could go, because there's two equally possible ways that it could go here and two equally possible ways it could go there. So there's a probability distribution that it hits that one, and that probability distribution has to reflect the fact that there's probable ways, two probable ways that it could go when it gets to one of those half-silvered mirrors. So that's really a probability distribution, and that's a probability distribution. Anyhow, so the neat thing is that we know that the server and the player have to be in the same reality. We also know that the virtual reality, the ones and zeros on the hard drive, okay, that reality cannot contain the player or the server. The server can't be in that computed reality because a simulation can't compute itself. So the elf, we'll talk about the elf, so the elf will never find the server inside of the World of Warcraft reality. It can't, because it's the server that creates that reality, so it has to be elsewhere, or Fredkin says, another, right? So it's the same with the player. The elf can never find the player that tells it what to do, that gives it all its choices inside the virtual reality. The player has to be outside, because from the elf's point of view, the player is non-physical and the computer is non-physical, because neither can be inside the World of Warcraft virtual reality, which is a bunch of ones and zeros on a hard drive. It's not alive, it's just a virtual reality. The player is an alive consciousness, interactive, and the computer is an interactive thing. Those two are interacting. So now, let's look at that. We live in a virtual reality. Okay? We, the body. Our consciousness has to be in some other reality frame. Our consciousness can't be here. Our consciousness can't be generated by a brain. That's like having the elf generate the player. The elf doesn't generate the player at the computer. The elf can't generate the server either, you see? So we don't generate consciousness anymore, and the elf generates its player. Now, if you're a World of Warcraft player and you sit there with your computer and your mouse and you make that elf do whatever you want, it's kind of silly to think that that elf is generating you. You're its consciousness, you make its choices, that's it, and you're trading information with the server. So now with this reality, here we are, we have these physical bodies, which are just like the elf. And we interact in this virtual reality because of its rule set, which is our physics, biology, chemistry, all the rules. That's the rule set of how this reality works. And just like the elf has a rule set, the elf can't walk through that tree. It's part of the rule set. The elf has to open doors to get into houses. The elf will drown if it stays underwater too long. It's the nature, it's the rule set of that World of Warcraft reality that those things happen to the elf. It's the nature that water runs downhill and that we can't jump 20 feet in the air. It's the way our biology is and our chemistry and our physics. So we live in this rule set. Our consciousness cannot be in this physical reality. It must be in a reality that's non-physical to us. To the elf, the only thing physical is the World of Warcraft reality, where the trees and the lakes and the water and the monsters and all that stuff is. The player's non-physical to the elf. The computer's non-physical to the elf. Well, the player, our consciousness, is non-physical to us from the viewpoint of our body. And the computer is invisible to us, is non-physical from the viewpoint of us in this virtual reality. That's the way it has to be. It's the nature of a virtual reality. So that tells us that our player is this consciousness. That's our awareness. That's the choice maker. It's the one that makes all of our choices. That's the consciousness. And that the larger consciousness system has to be in the same reality as our consciousness. So the consciousness and the consciousness computer, if you will, the larger consciousness system, the computer that is part of the larger conscious system, and the player that is part of the larger consciousness system, are all in the same reality system of consciousness. They're trading data. We, in this virtual reality, are just going through the motions. We're a calculation, what we do with our bodies, based on a rule set that allows us to let our consciousness make choices and then either evolve or de-evolve based on the quality of those choices. So we are an entropy reduction, consciousness evolution, virtual reality trainer, you see? So now that's, all those things kind of make sense. And the only data that the computer ever sends to the consciousness is when the consciousness needs a result from a choice that it's made. What's the effect of this choice? No choices are made, no data is sent. That's why it's a measurement problem. No measurement made, no particle exists. It's just probability. You make a measurement and they say, quote, the wave function collapse, and this is a probability wave. The probability collapses to a particle. What happens is that the server sends the consciousness some data that defines the result of this experiment, and that has to be in terms of a virtual result in this virtual world, and they get a particle and their detector. So that's how all of this connects, you see, and why it has to be that way.
My big toe theory has always stated and supported that this is a virtual reality.
Yes.
How significant is this delayed choice experiment by these people at Australian National University? How significant is this to finally cementing that idea that we are a virtual reality?
Well, that's an interesting question. Theoretically, this experiment is telling us something that we've already known for almost 100 years. Right? We knew in the early 1900s, when quantum mechanics was first being defined as a science, okay, by Bohr and Wigner and Heisenberg and Schrodinger. Einstein was part of that as well, although he disagreed with an awful lot of it, and he was wrong on that point. But anyway, we knew back in the early 1900s, certainly by the mid-1920s, that this was that the materialist model was wrong. Okay? They did not really understand how to describe it, because in those days, the concept of a digital computer didn't exist. The concept of a virtual reality didn't exist. These are concepts that were only thought of later, once computers actually existed. At that time, there were no computers. The idea of a computer hadn't even been dreamed up yet, even in a laboratory. So they didn't immediately go, aha, this must be a virtual reality, because that wasn't part of their decision space. It wasn't something they could think about. They didn't have the right fundamental understandings to come to that conclusion. But they did know that this material viewpoint, the materialism, the material reductionism, was just wrong. It wasn't correct. They tried to think about what could possibly be correct. They understood that it had to do with making the measurement. It's when you make the measurement that the particle exists. And this became known as the measurement problem. Because why should a particle exist because you make a measurement, you see? And in your sense, what you said is because you looked. You know, it's there because you look at it. You make a measurement. So you get the data. That was known to be a fact. It couldn't be explained. And the concepts that would explain it were many decades away. So you say, now, what's the significance? Well, the significance is that, one, John Wheeler, who finally, he started out, you know, he was with these guys. John Wheeler was a young man. He was one of the junior members of this group of you know, Heisenberg and Bohr and Einstein and the rest of them. He was there shoulder to shoulder with those guys, but he wasn't one of the old hands. He was one of the young guys. And in the beginning, he took the view that everything's particles, and he went through a couple of iterations of different viewpoints, but at the end, he was convinced that everything is information, that it is indeed a virtual reality. He didn't die until 2008. So he had the ideas of virtual realities and information and computing and all that sort of stuff. It was something now that he understood, and he put all that together. That's when he coined the term it from bit, the universe, the physical reality from information. Okay, a very bright guy. So one, this kind of verified that what he thought about reality, and here was an experiment to show it, turned out that it was right. This thing acts like information, not like particles. See, the probability is information. Particles are something different. They're hard little things in this reality. They're different. Okay, so that's one thing. It verified that that's a good idea that he had, that this is information. The experiment said, yea, verily, no particles, yes, information in the form of probability, which then quantum mechanics defines as probability waves, and then the probability waves collapse to make a particle. See, so that is good. The other thing is that when you did this experiment, it also showed that it wasn't just something quirky about the double slit experiment that produced these kinds of results. Well, here's another experiment that doesn't have any double slits in it, and the same stuff happens for the same reason. You see, it's just a different kind of experiment, which tells you that that kind of an effect is fundamental. It's not a quirk of this experimental setup. It's fundamental to reality. So that was an important thing that it did. But now let's look at it from more of a philosophical viewpoint. What is it a big deal or not? Well, probably not as big a deal as it should be. And that's because it has told physicists what they have actually known for almost 100 years. So they knew this in the 1920s, and now we're at 2015. It's almost 100 years have gone by, and they have known that materialism is wrong, and that this new idea of virtual reality answers all the mail. It answers the questions, it explains how the experiment works, it gets the right answers, and one of their very best, John Archibald Wheeler, you know, he was all the way behind it, and he was one of the better minds in physics. Like I say, a lot of the better minds in physics that followed were his students. So he was quite, you know, he was quite the man, quite the physicist, and he came to this conclusion. But anyway, physics, like anything else, is populated by people. And people everywhere run their lives out of their fear, their ego, their beliefs, and their expectations. That's just how they run their lives. And scientists, who are supposed to be in the pursuit of truth, often redefine the pursuit of truth as the pursuit of their beliefs. In other words, their beliefs must be true because that's their beliefs. They believe them. Well, if it doesn't suit their belief, if it's contrary to their belief, then it must not be true. It's just that simple, you see. So when they hear something like this, and it says, materialism isn't right, they go, yeah, well, I see that says that, but there's just something we don't understand yet. You know, this will all work out later. It's just a problem we don't understand. It looks like materialism isn't right, but we know it is. And that means, in psychological terms, that's called denial. They just deny the facts because, like they say, it's an inconvenient truth. If they admitted that, they'd have to admit that their whole basis of how they see the world is wrong. Their whole belief system that's been around since Newton is wrong. And they don't want to go there because they've invested their lives in this being a materialist, deterministic reality.
Well, you did say that Einstein didn't quite believe all of the findings of the Copenhagen, the Copenhagen interpretation. But he did say, this is an illusion, albeit a persistent one. Mm-hmm. Do you think he was referring to...
he did. As he got older and the experiments came in, Einstein wasn't a dumb guy, and he wasn't trapped by his beliefs. He saw that the things that he believed wouldn't happen, happened. The EPR experiments stand for three physicists who had some experiments. Einstein was one of them. Einstein was the E of the I think it was the ERP, Rosenberg and Podolsky experiments. Yeah. Anyway, they said entanglement will never happen. That's ridiculous. Of course, experiments showed that entanglement happened. So Einstein was not trapped by his beliefs, and he went back and said lots of things that indicated, wow, materialism isn't the right answer, but I have no idea what the right answer is. And he saw that you only got particles when you did measurements. And he looked at that and he said, well, that means that consciousness takes consciousness to make a measurement. Consciousness sends for the data. Well, that's right, it does. And when consciousness sends for the data, it gets some data, and the data is based on probability. And he knew all that, and he said, well, somewhere at the root of this, it has something to do with consciousness, but I have no idea what the fundamentals look like. And that's a quote that I give in one of my things from Einstein. I didn't quote it exactly, but I paraphrased it. It was something like that. So Einstein wasn't I deny it, it can't be that way, oh, they must have made a mistake. He wasn't that foolish. He said, yep, it's not the way I thought it is, and I have no idea. And of course, nobody else did either. At that time, nobody had any idea about how it might work. Because again, virtual reality was not a thinkable thought at that time. They just knew that it was probability, had to do with consciousness. They had all the pieces, but they didn't have the structure, the philosophical and the theoretical structure to hang it on. That didn't show up until later. That's why Wheeler, who was one of the young guys, he lived long enough that he got it. Later in life, in the beginning, he was with them. This can't be, something's wrong here. And then later in life, he saw the connection and said, yes, virtual reality, it from bit. And it surprised a lot of people because he stood out among physicists for two reasons. One, he was brighter and more productive than almost any of them. And two, he held these ridiculous ideas that couldn't possibly be right. Well, those two things don't go together. If you're a smart guy, your ideas aren't the ridiculous ones, you see. But that was, so this is kind of vindication, after his death, that he really was right all along. So when it comes to what effect is it going to have in the world of physics, well, what it's going to do is it drives one more nail in the coffin of materialism. But because the vast majority of scientists, not just physicists, biologists, chemists, physicians, left-brain people in the world, technical people, the majority of them believe life must be material and that somehow the brain creates consciousness. I mean, look at consciousness researchers. Every one of them that is academically viable, is working at a university and getting a paycheck from the university, are all trying to show how the physical reality creates consciousness. They're all trying to show how the elf creates the player. Now we look at that and we say, well, that's ridiculous. the elf doesn't create the player at the computer, and the elf doesn't create, the server. The elf is the product of those things. The elf's the product of the server, and it makes choices based on the player. And all of these consciousness researchers want to prove that the elf actually creates the player, because that's the materialistic answer. Material has to make everything else. So consciousness has to be a product of matter, you see. And with that belief, this experiment is just another annoying point that will someday have to be explained some way else, some other way, you see. And they just are not going to say, wow, okay, we get it now. It must be a virtual reality. Wow, everything I thought up to this point must be wrong. People don't do that. They're connected to their beliefs deeply, and they will deny evidence that that's contrary to those beliefs. They have been denying it for 100 years. No one expects another experiment. This is one out of probably 1,000 experiments. There's been thousands of these kinds of experiments that do this, and these aren't even expensive experiments. And thousands of experiments that do double slit, and they do double slit delayed erasers. This is a delayed eraser because you delay, the particle comes into this machine, and you delay whether you have a mirror here, and you're going to erase which way information by putting that mirror in until after the particle's in the machine. So anyway, these have been done probably 1,000 times. So you've got 1,000 experiments to prove that materialism is wrong, and yet it's still a minority of physicists that'll say materialism is wrong because it conflicts with their beliefs. So how important is it in the world of changing the minds of physicists? Probably not so much. Probably won't change very many minds. Everybody will just say, oh yeah, reality sure is strange, isn't it? Nobody will ever understand this stuff, why it works this way. It's probably just one of those things we'll never understand. And that's how they pass it off. That's their excuse for not having to deal with it.
Yeah, it's something you had said in a previous interview that we did, that this would be, the acceptance of this as a virtual reality would be the next paradigm shift for science. Yes,
you see, it's not just a scientific issue. It's not just, well, scientists should accept the facts as the experiments, deliver the facts. It goes much bigger. It's a philosophical issue that's very important to scientists. They'd probably give up the physics point if it wasn't for the philosophical issue. When you say reality is virtual and that it comes from other, as some scientists say, Fredkin said back in the 1995 or something, he said that. But if that's a general accepted thought, then the next thought is, well, if this is a virtual reality and it's computed, where's the computer and who's the programmer? Well, those are very rational questions. Physicists don't want to go there. They see who's the programmer and where's the computer as going back to the bad old days when the religious high priests were in charge, not the technical high priests being in charge. That's going back to them in the age of superstition and foolishness, you see? So their physics is taking them to a place that they can't go. They don't want to go. And that's why they're being so stubborn. It's not just that they're bad scientists and refuse to look at the facts. That's true. They are bad scientists because they refuse to look at the facts. But they don't want to look at the facts because they don't like the implications of the facts, that this is computed in a non-physical reality that must be non-physical to us because we're the virtual reality. Therefore, the server must be non-physical, and the player, the consciousness, our consciousness that makes the choice, must be non-physical. So now they're saying, oh, we people here, we're just the avatars. And the real us is in another reality frame that's non-physical to us. And the computer that set all this up is in a frame that's non-physical to us. Suddenly this non-physical reality is major and fundamental, and we here in this physical universe are a product of it and not fundamental. Ooh, that's what the Pope was trying to tell us in the 10th century, right? And we don't want to go back there. We don't want the religious wars. We don't want all that nonsense loose in the world. We like this deterministic material reality that we understand are in charge of, and we're not going to let it go just because some experiments are showing that it's wrong. You see? So that's their problem.
I think you
and it's because
said
they
it right.
because they don't see that in order to move forward, they have to accept that this is a virtual reality. But then they can understand it like I do in terms of my big toe. It's still science. We don't have to go to a little old man with a long white beard playing with his pet people who is also a great programmer. That's not the logical inference. It doesn't go there. It goes to a larger consciousness system that is aware, that is a digital information system that is trying to evolve. It's finite, it's not infinite, it's real, it's imperfect, and it's just trying to survive like anything else that's trying to evolve. It's just trying to adapt to its environment, internal and external. So that's what's going on. We're part of this system. We're a piece of this larger consciousness system. And how does a digital information system evolve? By lowering its entropy, by creating more information out of random bits. That's how you lower information, or lower your entropy if you're a system. That's how information systems evolve. And we are part of that evolution. We, not we the body, we the consciousness who are playing these body avatars, you see, we the consciousness are trying to make choices, and by those choices, we evolve our own individuated unit of consciousness, and since we're a part of the whole thing, we're helping the whole thing evolve. That's that kind of brings it back to why is it like this? Where does it come from? Who's the programmer? Well, the programmer is just a larger consciousness system. What's that? It's just a natural information system that is aware, and it's evolving. It's in a state of becoming, as are we, and it's changing, imperfect, real, finite system. So it doesn't lead to theology in the sense of the old days. What it does is it takes the theology of the old days and gets rid of all the dogma and all the creeds and all the belief stuff and turns it into something scientific, you see? So it's not that they should see science de-evolving back to the 10th century. They need to see that all that religion needs to evolve up to science that now understands the larger reality. And then it's more of one happy family then. It's not the scientists over here and the religious people over there, and they don't like each other and they think each other are fools and so on. It's not that combative thing. What it is that, oh, we get it now. Yeah, there's a larger consciousness system. Consciousness is a thing. It's non-physical to us. We have a non-physical part. Oh, what do we call that? Well, if you're religious, you call it a soul. If you're not religious, it's just a non-physical part, because that's our consciousness. We're just this avatar body. So now everybody starts to agree, and the only thing that gets left in the dust is the dogma, the creeds, the rituals. All of that stuff gets ejected because it doesn't play.
All the positive parts of people's beliefs are still there.
Right.
All of the different cultural aspects to what people experience or see as a
sure.
larger consciousness system is still there. It's just that this is a more cohesive, bigger picture view of it.
Yes, I asked a bunch of PhD theologists in Atlanta. We were in a panel together, and I asked them, I said, can you tell me what are the attributes of God that you, as you see it, as theologians? And these were all unity theologians, so they were not the most dogmatic type. They were probably the least dogmatic type. And they went out and they listed 5 or 6 or 8 or 10 attributes of God, and every one of them fit the description of the larger consciousness system, because they didn't have any attributes that were dogmatic. They didn't say things that were silly like, well, okay, God's a person that if you believe in him, he likes you, and if you don't believe in him, he doesn't like you. You see, that's just dogma. So they didn't say things like that, and the things they did say fit. So what happens is that religion and philosophy, the Buddha said, the physical world is maya, is illusion. Well, that's a virtual reality description if there ever was one, right? So you can take, in Christianity, God is love. Well, there it is. You take a consciousness, and a very low entropy consciousness is love. That's what love is. It's about other, not about self. So what it does is it takes the religion and the philosophy, both East and West, and gives it a scientific structure to understand what the Buddha meant when he said everything was illusion in this physical world. What it meant when he said God is love. What did all these things mean? And suddenly you get, oh, I get it. It's not a belief, it's science, it's logic. And then you find out that this model that I have of consciousness derives quantum mechanics. And it also derives relativity. It tells you why C is a constant. It also tells you why tunneling works and why entanglement and all those things work are no longer a mystery. And things that used to be paranormal, they're just normal now. Well, not necessarily all of them. Some paranormal stuff was probably silly stuff, but a lot of the things, the fundamental things that fell in the paranormal group, such as telepathy, such as mental healing, the placebo effect, all those things, telekinesis. There's a lot of things that have been studied, and all those things have become facts in a larger understanding. And you can also, so that same larger understanding says why those facts work sometimes and don't work sometimes, why they seem to be problematical in studying and so on. All of that comes out of it too. That's also logical. No, those things don't work the same way that this virtual reality works. They're based in a different reality frame. But anyway, everything comes out making sense. So that's kind of the nutshell, and that's why this is important, because it is one more nail in the coffin of materialism, and one day scientists will have to gather enough courage to move forward rather than continue to deny the facts of their experiments in order to stay still and stagnate in this concept of materialism instead of moving forward and not only liberating themselves and their science, but liberating philosophy and theology at the same time. You see?
Well, Tom, that's very interesting, and I hope that eventually that will happen. We've been speaking of an experiment done by Australian National University, and that is very recent, that is 2015. But back in 1999, there was another experiment that you're familiar with, a delayed choice quantum eraser experiment. This was done by physicists at the University of Maryland and Texas A&M University, Marlon Scully at Texas A&M University. A delayed choice experiment was proposed by Scully and Joule in 1982. Now, Kim and Kulik and Shi and Scully conducted this experiment in 1999. Tell me what you know about this experiment and also what the significance is of this.
Okay. This experiment is a delayed choice eraser. Just as this might be called a delayed choice eraser, the thing that Wheeler proposed. They're just two very different kinds of experiments. Now, what they did and why it was important was that back in the 1920s, when quantum mechanics was showing itself to be very weird, and when scientists were shaking their heads and trying to figure out a way that this could have a materialistic explanation so that it fit in like everything else, that was materialistic. They were looking for that very hard. Some of them proposed, they said, well, the reason that when you have the particles and you don't have which way information, that you get this probability distribution that is called the diffraction pattern. if you then measure the which way information, that diffraction pattern goes away. Okay? They call that decoherence. And that decoherence causes you to just get a pile of particles in a spot, one behind each slit. Okay? Now, that didn't seem to happen for any good materialistic reason. Okay? It happened for reasons that nobody could put their finger on, and it showed that because it happened that way, materialism was wrong. Well, a lot of people said, oh, we have to get out of this. We have to show that materialism is right. So what they came up with is that, well, when the detector measures which way which slit the particle goes through, when you get that which way information, the only way to possibly get that measurement of the particle going through the slit is you have to somehow interact with that particle. You have to bounce a photon off of it. You somehow have to sense it in a field. You have to interact with it. And when you interact with it, you can't help but nudge it, bump it, give a little energy to it, take a little energy away. There's no way that you can measure it without touching it, affecting it somehow. And they said, aha, that's the materialist way that it works. It's that touch on that particle when you make the measurement that creates the decoherence that destroys the interference pattern and just gives you the two spots behind each slit. So that was the idea, because that kind of saved materialism. And a whole lot of people jumped on that bandwagon because everybody dearly wanted to find a materialistic answer to this experiment. Well, the early researchers thought about that, calculated about that, did some experiments, and they said, it's true that we cannot eliminate interaction with the particle when we measure which slit it's in. But we have done experiments such that that interaction is so small and so slight that it couldn't possibly cause any difference in the experiment. And they say that is not a good reason. It's not a good explanation that there's some kind of physical interaction going with that particle upon measurement. And all the physicists who were specialists in quantum theory knew that. They all agreed to that. The textbooks that I read back in the 1960s said some people thought that interaction during the measurement, was what caused it, but we know that's not true. I read that in the 60s. It's not like this is, well, it was widespread because that was just the message all the physicists wanted to hear. So that theory that the particles hitting, or the interaction with the particle as it passed through the slit to measure it, that was the culprit causing this decoherence. That's why you lost the diffraction pattern, not because you somehow got information on the which way. Oh, that couldn't have anything to do with it. It was a physical thing, you see. Well, that spread through the physics community like wildfire because it was exactly what physicists wanted to hear. Problem solved. Everything's all right again in the world. Hallelujah. It's physical. Materialism is safe. That misinformation, that mistake, has been alive and circulating ever since. Now, again, quantum mechanics people like Feynman, who were really understood what they were doing, they knew better. They knew that wasn't the answer. They knew that didn't pull them out of the fire and rebuild a foundation under materialism. That's why Feynman was quoted as saying, shut up and calculate. Nobody can tell you why this works this way. You just calculate. He also said, nobody will ever understand how this double slit experiment works. It's just beyond understanding. Don't think anybody will ever know. It's just one of those things we're not meant to understand. So that's a cop-out, obviously, but that's Feynman. But he knew that this foolishness about, it's because the way we touch that particle when we measure it, that's the problem. He knew that was nonsense. And so does every other quantum physicist who is really a quantum physicist. Now, every physicist takes quantum mechanics, just like every doctor takes certain level of medical courses. But then some of them go on to be brain surgeons, some of them become, eye, ear, nose, and throat, some of them do bones, some of them do feet, some of them do skin, some of them do heart. They have specialties. Physics is like that too. And quantum mechanics is a specialty. And when some kind of new interesting information comes out in quantum mechanics, All the rest of the physicists don't necessarily know about it, hear about it, or even care about it. If some new great technique in brain surgery occurs, all the foot doctors and the dermatologists don't necessarily know about it or care about it. It's not their specialty. But they did get this kind of fundamental brush by it. All doctors find out how brains work, and they all find out how bones work, and they all find out how the skin works. So they all know some of the stuff. And most of them down at that level in the physics world still believe that materialism is king because the interaction during that measurement is what causes the decoherence. That's a favorite because nobody wants to let go of it. It's the only excuse they have to make materialism real and fundamental. So it's still a widely held position among those who really don't know the details because they're not really quantum physicists. All right, so, the caliber of Feynman had no sense that really it was materialistic of those particles. You never heard Feynman say anything that silly. He wouldn't say that. He knew better. He said, nobody will ever understand it. Well, if the way it worked was that touch during the measurement that created it, well, we'd understand it. It's that touch, it's that energy put on that particle. He wouldn't say what he said. He'd know the answer was materialism reigns and that was that touch, but he knew that wasn't it. That's why he didn't say that. He said it's a deep mystery, we'll never know. So when you get the quotes from the experts who know, then you don't find that kind of foolishness. But you do get it when you just ask a physicist who doesn't really know, because it's not his field of expertise. And he dearly wants to believe it, and so do most of his brethren, so that's what they tell each other. And that's what they believe. So this experiment that you mentioned was the first one that I know of that figured out a way to do the double slit experiment, get the which way data, and never touch the particle at all. No energy of any amount, zero energy, was ever touched that particle in the measurement process. And the reason for that is this experiment had the particles going through the double slits striking a material, and when they hit that material, they produced an entangled pair of photons. So something comes in, hits this material, two photons that are entangled go out. One of them went to the regular double slit for the double slit experiment. The other one was used as the which way information, the other entangled particle, you see. So now you could have a way of measuring the which way information without ever touching the particles that were going through the double slits. So that was, we finally got to that thing where we could measure the which way without any way interfering with, touching, or doing anything at all to the particles that were going through the double slits. And of course, what they found out was just what everybody knew all along, is that it had nothing to do with energy touching those particles causing decoherence, because they had the same decoherence when they lost the which way information of those particles that had never been touched. And at the end of the experiment, it was kind of, well, I guess we finally proved what we've all known for 100 years. So it was a little anticlimactic, but at the same time, it was the first time that there was no room for the naysayers and the people in denial to say, yeah, but okay, it doesn't make sense that would have anything to do, but it must be it, because otherwise there's no material explanation. So that has to be it.
So this experiment was 16 years ago. Materialism took a big hit.
16 years ago, the last hope of materialism to explain quantum mechanics was dashed on the rocks with this experiment. Okay. But I don't think it dampened their beliefs hardly at all. And because this was done in a quantum mechanics test, a lot of physicists never heard about it. You could probably query 100 physicists and say, have you ever heard of this experiment? Just random physicists. And my guess, out of 100, 90 of them would say, huh? What experiment? No, I never heard of it. Because it's not their field. They don't keep up with the details that are not in their field. It's too much. A doctor can't keep up with everything in brain surgery knee surgery, skin, internal medicine. They can't keep up with everything on the cutting edge. It's just too much information. They specialize. Well, it's the same in physics.
So if you could summarize the key point of this delayed
Well, this was a delayed eraser, which means they had the two particles going through the double slits, and again they interacted. If you did not have which way data from their what's called the idler particles, they had the signal particles and the idler particles. That's the two particles that are going to go through the double slits, and the two that are just the particles created by the entangled pair going off. When they got rid of the which way information, which means they didn't look at, they took these two entangled things and they put them through a thing that didn't allow them to tell which slit they came through. When they did that, then they didn't have which way information, they got a diffraction pattern. When they used these two entangled particles to tell them which way which particle went through which one, because they could do it with time. They knew that a particle hit, then there was going to be one that was going to hit up here, and something was going to hit down here. For each particle, you were going to get a hit out of the idlers and a hit out of the signals, because those two particles were hit for every one particle that went in. You see? So they could tell by the times which particles were associated with which. So the particles that the idlers said, oh, this went through slit A, then they know that that hit that just occurred up there must have come through that slit. So that gave them the which way information. So it worked exactly like they thought. When they had no which way information, they got diffraction patterns. When they did have which way information, they got two piles of particles. Then they did the experiment further. They made it such that the path in which they looked at the idler particles to determine the which way information was a much longer path than the one that went through the double slits into the screen. So the particle hits, the signal particles go up, go through the double slits, do whatever they're going to do, and make a point on the screen. It's done. Experiment's over. The idler particles, which carry the which way information, haven't been dealt with yet. They're still traveling along on this older path. And then later, even after that other one's gone through the double slit, you got a point somewhere, supposedly. Now they determine here whether or not they're going to keep the which way information or throw it away, erase it. That makes it a delayed eraser. It's delayed until after the experiment's already over. The data's already been collected at the double slit screen. So the data's been collected, now a decision's made, well, let's erase the data. And they find out that that point that was already collected falls on a distribution of, a diffraction pattern. Or they say, well, let's keep the which way data, and they find that that point that had already been collected happens to fall on a spot right behind each slit. And they go, wow, how could that happen? How could the data that we collected at the screen at the double slit was already old, and before we made the decision of where that point should go? The point was collected, and the data that would say where that slit ought to go hadn't been made yet. So it's a delayed reaction. And that then, of course, mystifies everybody, because it looks like backward causality. It looks like, well, we captured the signal data, it's gone through the double slits, it's hit the screen, the data's collected, that's done, and now we say, let's erase the which way data, and that data point we already collected is on a diffraction pattern line, you see. Whereas had they said the other thing, it would have been on a decoherence, just a two-pile line. So it's like backwards causality. We do this and it changes the result we've already taken. Well, that's because they're thinking materialism and particles. If you look at the probability, you'll see that the probability of the measurement isn't done yet. The probability of the measurement isn't done until somebody looks at the data. And nobody looks at the data until the experiment's over. They do all these experiments, then they look at the data and see. And every time they had which way data, they end up with two piles of particles. And every way they don't, they end up with a diffraction pattern. It doesn't matter how late they waited to decide whether they had which way data or not. Okay, so that's That's a delayed eraser. In a delay, after the data had been taken, they erased the which way information. So that is and they did that not with them having to meddle with the experiment, but they just let the probability do that for them. Because sometimes, half the time, you see it was these mirrors, the same kind of mirrors here, where the light can either bounce off or go through with a 50-50. Some of the time they went this way, and which way and if they did that, they got the which way information. Some of the time they went the other way, which means, they didn't get the which way information. So half the time they got it, half the time they didn't, and who knows when those were going to happen. That was just up to what the particle did. There wasn't a scientist really deciding that. It just decided that itself. So that was an experiment. It was a very elegant experiment, and it was clear that this idea about the thing that really makes this work is meddling with that particle when you take the measurement of the which way data. That was laid to rest. There was no interference with that particle.
So that was a very significant
It's a very significant finding.
It was 15 years ago.
15 years ago.
I'm sure, Tom, the scientists will find this very interesting. I find it very interesting. What could you tell the general public who may be listening to this video? What significance does it have for them?
Well, what it says is that, and what the double slit has said, and what all of these experiments have said, including the entanglement experiments, the tunneling experiments, all of these experiments defy a materialistic explanation. By that I mean they just flat out say materialism cannot explain this. The materialist view of reality is wrong. So that's what and they've been saying this since early 1900s. So now people are walking around thinking, well, that's pretty powerful. That's a pretty big deal that our whole material concept of the world is wrong. And we've known this for 100 years, and I've never even heard about it.
Should that be a frightening thing? I mean, how can that be?
Frightening thing depends on what side you're on. It's either a frightening thing or it's a funny thing.
How can that be a good thing for people?
Well, it's not. But science, like anything else, is belief-based. I mean, everybody's like it. Those brain surgeons are belief-based too. They have a belief in the way things work, and they work according to those beliefs. And when information is contrary to that, the first thing to do is deny it. Now, if it keeps coming, then maybe eventually you give in. But here, the stakes are too high. They're not just giving in to a better science. They're giving in to a non-physical reality that is more fundamental than the physical reality. That is a really big step to give into, and they don't want to let that go.
Well, let's speak to the people then. All right, the scientists will have to figure this out eventually, but to the people, your average people, what could this mean to them?
Well, what it means is that they don't live in a materialist reality. They do have free will. They are not a body. They are consciousness. They have a purpose. Their purpose is to lower the entropy of their consciousness. That's how a consciousness evolves. And what that means, and it's a very logical process that derives this, although we're not going through that now, just make the statement, but logic will show you that what that means is they need to become love. They need to become more caring. It needs to be more about other, not so much about themselves. That is the direction of consciousness evolution. And that's not my idea of what it ought to be. That's what the logic says. If you just work out the logic, that's a result. That's one of the logical results of this idea that derives quantum mechanics, relativity, theology. All of those things are derived out of this accurately, and the logic of this theory says that you are not your body, your consciousness. Your consciousness is non-physical. You have a non-physical part. People in religion for years have called that soul. That this non-physical part doesn't die. The body dies. It's like your elf dies. When you're playing World of Warcraft and you're sitting at your computer and your elf makes a bad move and some barbarian hits him over the head and your elf dies. The guy at the computer doesn't die. He's the consciousness. Just the elf dies. And what do? Well, you have to run back to the graveyard and you know, your elf pops back up and you run back out to where the battle was and you gather up all your equipment and all your stuff that's lying there with your body, and then you go on and continue to play the game. And it works pretty much that with consciousness too, because you have a mission here to grow up, and you can't do it. It's a difficult thing. You can't do it in just one game. You can't do it in one experience packet. So you do that, and then when the physical body dies, the consciousness will find another avatar to play another game, because he's going to have to play lots of games before he gets it and grows up, lets go of fear, and becomes love. It's not an easy thing to do. So anyway, it works very much the same. The fundamentals of virtual reality are the same all over. You see, so what the average person can find is all these things. They have a non-physical part. Their non-physical part doesn't die. It's immortal. That's only this elf, this virtual reality, these ones and zeros in a computer that define this. Yeah, that dies because the rule set, it gets old. When it gets old, things stop working, and eventually it dies, you know, and that's part of the logic of the system as well. There's a need for that. So
I think
a person
will get this.
So a person gets, he gets a lot out of seeing this. You say, what does the average person get out of it? Well, it means a whole different thing to their life. And the thing that's great about it is that it's not, it's not exclusive. Religious people can get it because they can see, oh yeah, it's just all the dogma that's nonsense. The fundamentals here, I get them. It's sort of what our religion was about, really, at the core anyway, you see. And all that dogma, well, we can just let that go. All the belief, all the hate, all the, my God's bigger than your God, all of that nonsense about we do it right and you do it wrong. You're going to let go of all that ego and foolishness. And the fundamentals, it's like all these theologians said, the fundamentals fit. Well, on the other end of that stick, the atheists can get it too. They can say, it's just like we told you. There isn't any little old man out there, that's playing with these pet people, moving things around and all this stuff. You got to believe this and you got to believe that. We knew that was all nonsense all along. Yeah, okay, and we'll see that, sure, it's a bigger reality, explains science better, and so on. They can get it too. It's totally non-exclusive. Everybody can play this game. The philosophers can get it because it gives something to them. A lot of things that they have been talking about for centuries suddenly make sense. Same as the theologians. Things they've been talking about for centuries suddenly make sense. Same with the scientists. The things they've been doing for 100 years suddenly make sense. Tunneling makes sense. Entanglement makes sense. Double slit makes sense. C being a constant makes sense. You see, so everybody can do this and it makes sense. What about the people who've had paranormal experiences? Oh, suddenly that makes sense. They're not crazy, they didn't imagine it. The world works that way when you understand that we have a non-physical component that's a consciousness that's growing up and so on. You understand how consciousness works, and that makes sense too. So we have lots of things, lots of people with lots of experiences that the larger society says, well, you must be making that up. You must be getting hysterical. You must have dreamed that, you see. That's not real. And the person knows inside, that was real. I was there. I experienced it. You don't believe it, but it was real. And they say, yeah, well, it just seemed real to you. And they're going, no, it was real. And, that people can use their intents to heal. Well, that's what the placebo effect does. Intent heals. Okay. Now, why does that work? Well, once you understand how conscious works, that's just a logical outcome. It has to. There's no other way it works. Just like particles have to be probability distributions. There's no other way it can work. So what does the average person get out of this is a whole new lease on existence. Why they're here, what they're doing, what the point is, and therefore they can get better at getting that point and doing what they're here for. They can, all of their experience, that is objective, and all of that is subjective now has a structure that makes sense. All that subjective stuff makes sense. Why they're miserable, why they're unhappy, why their life sucks, why it's such a struggle being here. It all makes sense. What they have to do to be happy, fulfilled, full of joy, enjoy life. That's all comes out of the logic too. And it all just makes sense. You see? So when you say, well, you know, okay, the scientists don't get it, but what's in it for everybody else? Well, that's there for the scientists and for everybody else. And it's life-changing. It's totally rewrites your whole sense of who you are and why you're here.
You certainly had a lot of comments from people that said my big toe theory is life-changing.
Yes, I've had thousands of people say that it's life-changing.
And I love that about it, and also that what you said about it is all inclusive. It includes everyone and everything.
Yeah, there are no losers.
Yeah.
You see, there are no losers.
There's no...
Everybody gets an explanation about life, and the only losers are the people who are so tied to their beliefs that they're trapped in those beliefs. They will lose those beliefs because those beliefs are not right. So the belief in materialism, the belief in the little old man God who plays with his pet people and who only will like you if you like him, you know, if you serve him and pray to him, you know, people who have these beliefs, you might say they're losers, but I call them winners. They have a chance to let go of that, you know, debilitating, trapping belief and go beyond it. They're not stuck anymore.
And they're not losing their God, because MBT science derives God. In a sense, you call it the larger consciousness system. But your science, in fact, derives God. You simply don't give it that title because you have respect for people's different viewpoints of that God.
Yes, if you call that God, then there'll be a lot of people who have all sorts of meanings about what that is, and you can't claim, well, I've just derived God, because that word God means so many things to so many people. All you're going to do is start a big argument that will be totally useless. So I derive the larger consciousness system, and that system has attributes of what these theologians thought were God, but it doesn't have the attributes that other people. It's not perfect. It's not infinite. It's evolving. It's not fixed, non-changing. It's changing too. So it's a real system. It's just a real system, evolving like real systems do. So in that sense, I wouldn't call it God, because it's not what a lot of people, maybe even most people, think about. But does it derive? Is this a derivation of an entity that performs all of the kind of fundamental and useful aspects attributed to a God? And yes, it does that. So in that way, you would say that MBT derives God, logically, as science. But you wouldn't say that if you took a normal, everyday definition of God, which is different. The things you believe will, get you into heaven and into hell and all this dogma stuff, and none of that is like that. You don't have that kind of stuff. You just are here, you're trying to grow up and evolve with your choices, and you make a little progress or you make a little regress, and then you try again, and so on. That's pretty much all there is to it. That's a very simple description, but that's it. There's not any dogma.
It's a very simple one, but
yeah,
a very good one.
It's very simple ideas. So, yes, it's very inclusive. If people would let go of those belief traps, they'd find a place in this that really answered the fundamental needs in their life. But if they want to cling to those belief traps, then they'll be fighting with their shadow. It's something they can't win, because this is actually the way the world seems to work. Now, I hasten to say that this is a theory. Everything in science is a theory. Quantum mechanics is the theory of quantum mechanics, and the theory of relativity, you see, and the theory of evolution, and the theory of certain kinds of chemistry, and the theories in biology. We don't have physical laws. We don't have proofs in science anymore. That was an old, you got to go back 200 years before people said, how do you prove that? Well, there's only two things you can prove, and one of them is logic. There are logic proofs. Okay, here's a logic proof, and it's an accurate proof. You come up with a statement like, all cows can fly. Bossy is a cow, therefore Bossy can fly. That's true. You see, based on the assumption, we have truth, and that is proof. That's proof. That's considered a logical proof that Bossy can fly, because Bossy's a cow, and we started with the assumption that all cows can fly. Now, of course, our assumption doesn't make any sense, but neither does an assumption of materialism make any sense. You see, but you can pick something nonsense, or nor does an idea about God playing with these pet people make any sense. So there's things, if you start out with a bad assumption, you logically can prove a bad result. So that's proof. And mathematics is just the logic of number. It's the logic of quantity. So there are proofs in mathematics where you can start here and logically get there. And if you show all the steps in between and you don't make any mistakes, that's a proof. But other than that, there are no proofs in science. We have theories, and we collect evidence. And when you have enough evidence, you begin to think that the theory is correct. So quantum mechanics, the theory of quantum mechanics, has been producing right answers and right calculations. Just like Feynman said, shut up and calculate. They've been calculating like crazy now for almost 100 years, and they're really good at it, and they are very successful. They can tell you just exactly the way those particles are going to act with their calculations. They're right. They're not only right some of the time, they're always right when they do the calculations right. But we don't call that a law, and we don't call that proof. We say that's a lot of good evidence. And the reason that we won't call it a law or a proof is because all the evidence hasn't come in yet. What are they going to find out in the next 100 years? Or the 100 years after that? So it takes a lot of arrogance and hubris to say, this is a law, we know everything can possibly be known about this, when there's a whole lot more that can probably be known about that, and you just don't understand it yet. We're always ignorant of what we're ignorant of. So we've given up that kind of hubris after Newton. We had Newton's laws, and then we found out that Newton's laws weren't laws at all. They weren't even right. They were close. They were a good approximation, but they don't do it right. You have to take relativity into account and quantum mechanics into account, and that old Newton stuff that was laws aren't laws, and everybody kind of thought, that's a bad idea. We need to get rid of this proof law thing, because that tells you that you're so arrogant you think that nobody will ever know more than you know now. And that's just a bad assumption. Look at history. That's always been a bad assumption. So there is, it's not about proof, it's about evidence. And there's a whole lot of evidence to back up MBT. So it's still a theory. And there may be parts of it that are still wrong. And even though a lot of it is verified by theory, that may turn out to be not complete or wrong in some other way. So it's not that it's perfect and complete, it's just that it's the only thing around that actually gives a bigger picture of everything and can derive quantum mechanics, relativity, theology, and philosophy all out of the same set of understandings.
It is the only thing around still, and I think your MET theory is the best thing we have.
Just a theory. And I also then would like to caution people, don't believe this theory. Don't believe in MBT. Don't believe in this theory at all. Belief is the enemy. Belief isn't any good. This can't be your truth if it's not your experience. Now, we can test the objective part. That's the quantum mechanics and the relativity and things, okay? And I'm coming up with a whole list of experiments that can be done to verify this. Well, that's just the objective part. But now there's a subjective part. It's also a theory that explains all of your subjective experiences, because those are experiences of consciousness. And if you understand consciousness, then you have a construct in which you can understand your subjective experiences, you see? So those have to be your personal experiences. That's what I mean by it can't be your truth if it's not your experience. So you don't want to believe it. You want to go find out for yourself. You want to experience it. You want to experience this larger reality and how it works. And it's not that hard to do. And anybody can learn how to do that. So this is not a thing to believe in. It's a thing to think about. It's a thing to be skeptical about. And it's a thing to decide, well, okay, I'll give it a 50% maybe. It might be right, but it might not. Let me go find out. Let me do some study. Let me see how well it fits science and physics. And let's see how well it fits my own personal subjective experience. And if it fits it, well, then maybe I'll raise it up to 60 or 70%. And if it doesn't, I'll throw it out as garbage. And that is the way that you should approach this idea. It ought to be experimental. You need to do your own work and not believe what people tell you. Be your own scientist. So that's an important part of it. I don't want people to think that I'm saying this is the theory that tells everything. This is the theory of everything, and there isn't anything else. Just believe this and you'll be okay. Don't believe this, because if you do, you won't be okay. You won't learn anything. As soon as you believe something, you stop asking questions. You stop being an experimentalist. You stop learning. So belief is the problem, not the solution.
Thank you so much, Tom. I think that the phrase that you just gave out, be your own scientist, is a great way to end this interview. And I think that's great advice. Thank you so much.
Well, thank you, Donna. It's been fun as usual.